Hello, welcome to another module in this massive open online course on Bayesian MMSE estimation for wireless communications. Alright. So, we are looking at the MMSE or the minimum mean squared error of wireless channel estimation. Alright. So, we are looking at the MMSE, that is the minimum mean squared error for your wireless channel estimation, correct. That is what we have been looking at in the previous module, okay. And we have derived the expression where h is the channel coefficient of the MMSE, the minimum mean square expected h hat minus h whole square. This is equal to the harmonic mean of the ML mean square error, but it is 1 over sigma square divided by norm x bar square plus 1 over sigma h square, which is the prior variance. So, this we said this is the MSE of the maximum likelihood estimate. And this is the prior variance. Okay, this is the MSE of the maximum likelihood estimate and the prior variance. Okay. So, and also we said this also valid, by the way, we said this is also expression also valid for a complex parameter, that is when the channel coefficient h is a complex quantity. Okay. So, this is also valid for MMSE of a complex channel coefficient h, except in that case the MMSE will be, the minimum mean squared error will be, we cannot simply use expected value of h hat minus h square, it will be expected value of magnitude h hat minus h whole square. Since it is a complex quantity, naturally we have to consider the magnitude, expected value not of the quantity square, expected value of the magnitude h hat minus h whole square, and that will be given by this expression. Alright. We are going to look at the estimation or the properties of the estimation of a complex channel coefficient shortly, that is we are going to look at more properties of the nature of the estimate of this complex channel coefficient shortly. Alright. But meanwhile, let us do an example. First, let us do an example to understand, just look at how this is used in principle, and then we will proceed to the other aspects. Okay. So, now let us consider a simple example. For instance, for a channel estimation scenario, again we go back to the example that we have considered previously. I want to consider n equal to 4 pilot symbols. Our pilot vector x bar equals, x bar will be 1 plus j, 1 minus j, 2 minus j, 1 plus 2 j. This is something that we already seen. And y bar, this is the observation vector, this is your 3 plus 5 j minus 5 minus 3 j, 2 plus 3 j minus 3 minus 2 j. This is our observation vector. So, this is our pilot vector, correct. This is our pilot vector, this is your observation vector. Okay. Now, let us say h is a complex channel coefficient, h is distributed as complex Gaussian, this symbol Cn, we use n for Gaussian, this symbol, this denotes complex Gaussian, okay, and we will talk more about this shortly. So, this is a complex Gaussian or a complex normal random variable. So, H is a complex channel coefficient, okay. So, this is H is a complex, is also known as, when it is complex Gaussian, this is also known as a Rayleigh fading channel coefficient. So, this is a complex this is your complex coefficient, let us say. Okay, complex normal distributed with mean 1 plus j, which is a complex coefficient. So, the mean is also complex, but the variance is always going to be a real quantity, right. Variance is always, because variance is defined as expected value of the magnitude of h minus mu h square. This is the expected value of the magnitude square, which in this case is expected value of magnitude of h minus 1 plus j whole square. This is your variance, that is sigma h square. Okay. So, the variance is basically the expected value of the magnitude square, alright. So, since the variance is the expected value of the magnitude square, the variance is always real, even for a complex normal distributed, correct. Even for a complex Gaussian random variable, the variance is real, it is just that the mean can now be a complex quantity, that is the expected value of h. The mean is simply the expected value of h or the average value of the fading channel coefficient. So, this can still be a complex quantity. So, the variance always has to be a real quantity, alright. And now, what we need also, let us say the noise variance sigma square dB, the dB noise variance, this is again something that we already have, that is 3 dB. This implies 10 log 10 sigma square equal to 3. This implies, that is your dB noise variance is basically 3 dB. This implies sigma square equals 10 to the power of 0.3, which is approximately equal to 2. 3 dB corresponds to a noise variance of basically 2. This is a standard result in communication, or a standard sort of rule of thumb which is often used, that is 3 dB corresponds to 2, therefore 6 dB corresponds to 4, minus 3 dB corresponds to half, and so on, alright. So, you should be familiar with these kinds of simple rules, or simple kinds of rules of thumb rather, that are used in analysis of examples and problems related to communication systems, okay. And norm x square, now what we need is the norm x bar, we have the pilot vector. Now, we need to calculate the MMSE, you know we need norm x bar square. This will be magnitude of some squares of the magnitude of all the pilot symbols, magnitude 1 plus j square plus magnitude 1 minus j square plus magnitude 2 minus j square plus magnitude 1 plus 2j square, which is equal to 2 plus 2 plus 5 plus 5, this is equal to 14. Okay. Now, we have the expression for the MSE. Expression for the MSE is expected value of, because this is a complex coefficient, we are using the magnitude. Okay. Remember, this is because you have to use the magnitude, because h is a complex coefficient. Okay, and this will be equal to 1 over sigma square divided by norm x bar square plus 1 over sigma h square. It is a very simple expression. Therefore, what we have is, in fact, we had spent quite some time, right, to simplify the complex expression we had to arrive at this simple expression, and this simple expression we already also said is very insightful because it yields several insights. It is a linear, it is a harmonic mean of the ML, the mean square error of the ML estimate and also the prior variance. So, now I substitute the quantities. Sigma square is 2 divided by norm x bar square, this is 14 plus 1 over sigma h square, this is the prior variance which is 1. This is equal to 1 divided by 7 plus 1, which is equal to 1 divided by 8, and this is your expected value of magnitude h hat minus h whole square. Okay, this is the minimum mean squared error, and this is basically your minimum mean squared error. This is basically your minimum mean squared error for the MMSE estimate of the channel coefficient H, of the feeding channel coefficient H for this given scenario. Okay. So, now we have shown an example, we have completed this example. We have illustrated how to compute this minimum mean squared error for the estimation of the complex channel coefficient H. All right. Now, let us look at some other properties of this estimate, this complex estimate of the complex feeding channel coefficient H. All right. Now, we know that H is a complex channel coefficient, therefore, it has a real part and an imaginary part. So, what we want to see is we want to characterize the properties of this complex estimate, all right, try to understand it better. Since so, estimation, so let us title this section as estimation of complex estimation of complex parameters. So, what we want to do is we want to consider estimation of a complex parameter. Remember, we said this coefficient, this h we are trying to estimate is a parameter. Now, because it is complex in nature, it becomes a complex parameter. So, consider the estimation of a complex. So, consider the estimation of a complex parameter h. Estimation of a complex parameter h. Now, since h is complex, correct, h will have naturally, since this is a complex, this is going to have a real part and also an imaginary part. This has both real and imaginary parts. So, I can represent h as h equals HR plus J times HI, where HR, this is the real part, of course, everyone, this is fairly obvious, this is your real part, and this is your imaginary part. This is the imaginary part, correct. And now, naturally, now we are going to assume this H is complex Gaussian, that is what we are saying. So, H is complex Gaussian, that is complex Gaussian. In addition, we are also going to assume that H is a symmetric complex 0 mean H is a symmetric complex Gaussian quantity. I am going to explain it. H is a symmetric, it is not just complex Gaussian, symmetric complex, symmetric complex Gaussian in the sense that if H is complex Gaussian with mean mu H and variance sigma H square, then it satisfies the following properties. The real part, of course, it is symmetric, therefore, the real part, the mean of the real part equals the mean of the imaginary part, correct, mean of the real part equals mean of the imaginary part, which is basically equal to half of the complex, which is basically the mean of the sorry. So, we have the mean of the real part which is equal to the real part of the mean, for instance expected value of HR equals the real part of the mean. This is of course obvious, expected value of the imaginary part equals the imaginary part of the mean. Further, if you look at the variances of the real part and imaginary part, that is, if you look at the expected value of HR, let us call this as real part of the mean, let us call this as mu r, and this let us call this as mu I, the imaginary mean. So, HR minus mu r whole square equals sigma H square by 2, that is, it has half the variance, and the imaginary part also has half the variance. So, it is a symmetric complex Gaussian, therefore, the mean of the real part is equal to the mean of the real part, mean of HR is equal to the real part of the mean, real part of mu H. The mean of the imaginary part is basically the imaginary part of the mean, okay. And the variances of the real part and imaginary part are both, they are both equal, correct. The variances of the real part, imaginary part are both equal, and they are both equal to sigma H square divided by 2. Further we are going to assume further the real part and the imaginary part are uncorrelated. In this case, since they are both Gaussian, they are also independent. So, expected value of HR minus mu r times HI minus mu I equal to 0, okay, which means these HR comma HI, these quantities HR comma HI, these are both Gaussian and each has variance equals half sigma H square, and more importantly these are, since they are Gaussian, these are uncorrelated, but since they are Gaussian, uncorrelated also implies that they are independent. Now, normally for any two random variables which are uncorrelated does not mean that they are independent, but in this case, since HR and HI, the real part is Gaussian, the imaginary part is Gaussian, they are both also uncorrelated, correct. So, naturally means that in this case they are both independent, alright. So, that is known as a symmetric complex Gaussian random variable, in which the real part and imaginary parts have basically identical variance and they are independent, alright. Now, let us also assume that the noise Vk, the noise Vk is 0 mean symmetric complex Gaussian. Symmetric complex Gaussian, which also again implies that if you have the real part of the noise, since it is 0 mean, equals imaginary part of the noise, both have 0 mean, and the variance, more importantly, expected VR square of k equals expected Vi square of k equals sigma square root. That is, both the real part and imaginary part have half the noise variance. So, the noise is also 0 mean. So, the noise is also complex, symmetric complex Gaussian. In addition, the noise we are saying is also 0 mean. So, this can be represented as complex Gaussian, 0 mean, variance sigma square. Okay. Now, in this case, let h hat be the estimate, is the estimate of the h hat be the estimate of the complex feeding coefficient. Now, naturally, since h hat is a complex, h hat is the estimate of a complex quantity, h hat is also going to be a complex quantity. Therefore, h hat will also have a real part and an imaginary part, that is real part of the estimate and imaginary part of the estimate. So, I can represent this as h hat of r plus j h hat of I, h hat of r plus j h hat of I. Okay. And now, we can show that the MSE or the minimum mean square error of each of these parts, the real part and imaginary part, that is, if you calculate these MMSEs h hat of r minus h of r whole square, this will be equal to the MMSE of the imaginary part, that is h hat of I minus h of I whole square, and these will be equal to half the total minimum mean squared error, and we know what is the minimum mean squared error. So, this will be a half of 1 over 1 over sigma square divided by norm x bar square plus 1 over sigma h square. So, this is the MMSE of the real part. This is the MMSE of the imaginary part. And this is your actual MMSE, or you can also call this as the total MMSE. So, what we are seeing, what we are saying is that the MMSE of the real part and the MMSE of the imaginary part, that is, we treat the real estimate of the real part separately, estimate of the imaginary part separately. If we consider the real estimate and the imaginary estimates separately, then each of them, the MMSE of each of them will be half the total MMSE that we have derived before. And more importantly, the estimation errors are going to be uncorrelated. That is, if you look at the estimation error of the real part, h hat r minus h r equals estimation error of real part, correct, h hat, and then we also have h hat I. This is equal to estimation error this is the estimation error of the imaginary part. And these two things, these are uncorrelated. For a general scenario, these are uncorrelated. However, since both of these are Gaussian, we have HR Gaussian, HI is also Gaussian, the estimates H hat R, H hat I are also Gaussian, since it is a Gaussian estimation scenario. Therefore, the estimation errors are also Gaussian, and these are therefore, since they are uncorrelated, they are also independent. Alright, implies also in their independence, since I have to qualify this statement, since they are, this is not always true because they are independent. So, that means that basically what we have is H hat, that is if you look at this H hat R minus H R into H hat I minus H I, this is going to be equal to, this is going to be equal to 0. Okay. So, the estimation errors are basically, the estimation errors are uncorrelated, or in this case also independent, since they are Gaussian. Okay. So, this is the property that the estimation errors, this is the estimation error of the real part, this is the estimation H hat R minus R, H R estimation error of the real part, H hat I minus H I is the estimation of the estimation error of the imaginary part, and therefore, the expected value of H hat R minus H R times H hat I minus H I is equal to 0. Okay. So, that is the property that we have. Alright. So, basically this gives you some more insight into the estimation of a complex channel coefficient. What we have said is basically the same principle, alright, and that is what we have already said even during the derivation of the MMSE estimate of the complex feeding channel coefficient, but just by replacing the transpose by the Hermitian, we can say that the principle or the formula of MMSE estimate for the complex for the feeding channel coefficient H can be extended to that of estimation of a complex feeding channel coefficient H. Further, we have said that this expression that we have derived for the MMSE, the minimum mean squared error, can also be extended in a straightforward fashion, except realizing that the MMSE is now going to be not just expected value of H hat minus H whole square, but expected value of magnitude H hat minus H square. Okay. And what we have said is, if we consider all the Gaussian random variables to be complex Gaussian, symmetric complex Gaussian, which means the real part and imaginary part are have equal variances, the noise is 0 mean. Further, the real part and the imaginary part are uncorrelated, or basically since they are Gaussian independent, then what we have seen is that the estimate, the variance of the estimate of the real part is equal to the variance of the estimate of the or the MMSE of the estimate of the real part is equal to the MMSE of the estimate of the imaginary part is equal to the half the total MMSE, and also the errors, the estimation errors of the real part and imaginary part are uncorrelated. Being Gaussian in this scenario, they are also independent. Right. So, that gives you more insights. So, naturally, so what we have said, with slight modification we can extend the principles and the results of estimation of real parameters to that for a complex parameter, and therefore, we are not going to elaborately consider the estimation, the specific rule for the estimation of a complex parameter or the MMSE for the estimation of the complex parameter in future modules, but it is expected that you understand it based on this intuition that the variance of the real and imaginary parts are going to be half the total MMSE for a symmetric complex Gaussian scenario, and also the estimation errors of the real and imaginary parts are independent for a Gaussian estimation scenario. Thank you. Thanks very much.